who is paying one-day working visit to our school and short visit to Singapore on way from Australia, Melbourne,
yes,
to Cape Town for ICSI. Prof. Jazayeri is a founding dean of the Faculty of Informatics at the University of Lugano since October 2004. He started career as assistant professor at the University of North Carolina, then left university and worked for several startup companies in Silicon Valley. Later joined Hewlett-Packard Labs in Palo Alto for 10 years. After that, he was leading the Distributed Systems Group at the Technical University of Vienna, also for 10 years. So you like go in 10 decades. Easy to count. And yeah, I had a great pleasure to visit him and his group during my sabbatical, which was December 98. Gee, it was 11 years ago. Difficult to imagine. 12. Yeah. Mehdi is a well-known figure in software engineering community. He was a program chair in all major software engineering conferences, gave keynote talks, ICSI, ESSEC, Foundations of Software Engineering, main software engineering forums. He also wrote, together with Carlo Ghezzi and Dino Mandrioli, an influential book on fundamentals of software engineering. So today, Prof. Jazayeri will be talking about, I understand, some difficulties to use principled approach in software development practice. And because of his knowledge of real world, and at the same time, understanding of principles of software engineering, I use this book, and I must say that that's the only book that talks about software engineering principles deeply, in comprehensive way, and throughout the whole book. I didn't find any other book who would be based on the principles. So he knows both real world and principles, so he is the best qualified person to talk about this. So now I think the floor is yours.
all right.
And we
And this, I guess I should, yeah. It feels like I'm a cyberman. So, good morning. Thank you very much, Stan, for the nice introduction. I'm very happy to be here. I've heard about NUS for a long time, and this is my first time here. I also remember when you visited us in Vienna, and that was a very memorable visit as well. So I've, since I'm on sabbatical this semester, I decided to think back and talk and think more generally about what we do in software engineering and what are some lessons about software engineering that we can share with others, not only software engineers. So how many of you are in software engineering? Almost all. And how many of you are not in software engineering? Don't consider yourself to be in software engineering. Okay, one. All right. So, well, that's okay. We can then it's an easy audience because I want to talk badly about people who are not in software engineering and say how they can learn from software engineering principles and ideas that we have developed. By we, I mean people in software engineering. So I'd like to start by saying that software is really critical to the working function of societies today, at least modern Western, well, not even Western, modern societies. We really depend on software to work. Everything is pervasive. All of our services, devices work with software. Without software, actually, the world would stop as we know it. It's not as important as the volcano. It can't stop things like that, but many things would have trouble without software. And what is strange is that despite the pervasiveness of software and its criticality, most people actually don't know much about software. Because the software just works and it stays out of the way. It just makes things work and doesn't complain, doesn't squeak, doesn't things don't fall out. It just works. So the question is, how is it that in such a short time, since 1968, we have been able to achieve so much with software? How come software has evolved so quickly, so well, that it's just the foundation now for many services, most services of society? And I think that software engineering is about understanding problems and implementing some solutions to these problems, understanding the problem, finding solutions that work economically now and forever. I mean, that's when we talk about how do we solve this problem. One of the difficulties is how do we make sure that the solution will evolve to meet future needs. So to do this, we have developed an approach to thinking about problems and to look for near-perfect solutions. And you'd think that people would actually really appreciate this, that software engineers are great because they've done so much and they can develop solutions like that. Unfortunately, in the real world, it's not really like that. Managers, for example, don't really like a software engineer to say, oh, no, this project will take longer than you promised, and it will cost more than you promised. Managers don't like that. Even within our own computer science community, informatics community, other people who work in other things, like I've had experiences with computational scientists, people who work on scientific computing, they don't really care that, if you tell them, oh, your software is not going to work when there's the next version of the operating system or the next version of the compiler or another computer architecture, they don't care. They just want to run their software and have the results. That's all. So again, they say, oh, come on, these software engineers are just giving us problems by telling us how to do things systematically. That's not, they don't really care about that. Worse than that is among lay people, normal, non-computer people, it's even worse. If because as a software engineer, you always try to think of problems. How do you solve this problem? How do you make sure that this problem doesn't occur again? And try telling that to people. If somebody is doing their job and you say, oh, you can do this better, they don't like that. They really don't like that. So, so that's the problem. So what I want to do in this talk is talk about some fundamental principles about software engineering that I think these principles are more general than just applying to software. They really apply in other disciplines as well, and I think it would be useful if we could communicate these ideas to other disciplines as well. As I said, unfortunately, doing this carelessly makes you unpopular with people, but it's worth a try. So I hope that, well, there's not many non-software engineering people here, but I hope that the talk will be also useful for them. So, of course, as you know, being in software engineering, software was not always so successful. In fact, at the beginning, the reason software engineering, the term was invented, was because there was a software crisis. We heard more about software crisis than software engineering. There were total disasters. Many projects failed in the 60s and early 70s. Almost any big project, you were sure that it was going to fail. So since the end of the 60s, we've been trying to figure out how to do things better. And one of the things we've done is to try to look at other disciplines that we think are more successful, and say, how do they do it? Let us copy what they do. And in fact, the word engineering was picked because people said, well, we're not doing computer science, we're doing engineering. So let's look at how engineers do things and copy what they do. What I'm going to do today actually is the opposite. I'm going to say, here's the kind of things we do in software engineering, and we do it very well. How can other people copy us? Because, superficially, one of the things people did was to say, let's copy architecture, building architecture, or civil engineering. Because superficially, a house consists of components like rooms and doors and things like that, and software has components. So let's apply some of those principles to us. And I think that's really only superficial. So I'm going to turn things around and talk in the other way. So, as I said, this thing of looking for problems doesn't make you popular, and we always run into problems when we do that. First thing, because we can't even say what software is. Okay, so in fact, if you think about it, what is software? It's really not such a trivial question, because we have so many representations of the software, and the software runs. And that's another thing. That's, is the thing that's running software? Is it the bits? Is it the electrons traveling, or what? And, as you can see, we have most people think that is software, because that's where the stuff is from which they install. At least they used to install like that. So it's pretty difficult to try to talk to people about software and, why what we have achieved is such a big deal. Other things, like buildings, you can see if there's something wrong, you can see it. Whereas with software, we can't see it. That's why we have developed techniques to look for problems. You can't just touch it and say, oh, this thing moves. We have to find really ways to deal with this really abstract object, to look for problems. So let me tell you the first anecdote of this talk. So as Stan said, I was the dean of the faculty, and one time the secretary brought me a form to sign. And this was a typical form that comes all the time, and it says, this person is the PhD supervisor of this other student, And I looked at the form, and I knew there was a mistake there, because in fact, I was the supervisor of the student, but the form said something else. Someone else was the supervisor. So, it was very easy as a as dean, it was very easy to just correct it, sign it, and give the form back. But as a software engineer, I can't do that. You have to say, how did this bug get in there? It's a bug. It's not just a typo. It's not just a clerical error. You have to know where this error came from. And so, I asked the secretary to contact the administration and say they should check their database. Well, of course, the administration didn't like that, because they said just fix the form and sign it. My secretary didn't like it, because she was caught between two things. And so, what am I going to do? I can either be unpopular and insist on the right thing, which is check the whole database, or go along and just sign the form and fix it. So in software engineering, if we want to build services that society depends on, we can't take that approach and just fix it. We have to look for the real cause and fix the real problem. In fact, one of the maybe simplest and perhaps deepest ideas at the bottom of software engineering, that leads to software reliability, is what Edgar Dijkstra said back in, I think even 69, 68. And he said that you can't just, if you test, it's great to test software. You can test software as much as you want, and it's great. You find bugs. But no matter how much you test, you cannot say that there are no more bugs left. So we have to be much more vigilant, much more careful about looking for bugs. It's not just because I didn't find it, it's not there. It's not enough. So this thing, guides the practice of software engineering, the effort to find reliable software. So we have to look for ways to find the bugs, find how they got there, and then fix that reason. And that reason might be much more complicated than just changing a name in a form. Well, this idea of finding bugs was also a problem back then, among software engineers, because you find you run somebody's program, and you say, oh, this has a bug. You did this, and so at that time, actually, there was a personal relationship between code and the person. People felt the code was their property. They didn't want to share it. And again, back then, in 1971, Gerald Weinberg wrote a book called Egoless Psychology of Computer Programming, and he promoted the idea of egoless programming. What he said was, software is not your property. It's not you. Actually, software development is a social activity. We all have to help to find the problems in the software. And as I said, he termed the phrase egoless programming. It's not you. It's not your ego that is at stake here. So we have to accept that there will be bugs. We have to have peer reviews, our own peers reviewing our code, trying to help us find the bugs, and then we fix them. So we have to be open to suggestions for change. What he was saying, again, was that software engineering, software development is a social activity. We all are at stake. We all have a stake in this endeavor. So I think this was a very, even though it was a popular book for a while, but it has lost its popularity, I think it was a very deep point. And in fact, recent developments, open source, extreme programming, agile development, really owe their psychological roots to this work by Weinberg. So my question is are there other disciplines, other things that could benefit from this approach of egoless programming or egoless development? And yes, my answer is yes. So of course, yeah. So architecture, building architecture. I don't know. Singapore is my first time here. It's very amazing, all these buildings going up. So I don't know if the experiences here are different. Perhaps this is a biased indictment of architects. But anyway, I will try it, and you can tell me if it doesn't apply in Singapore. So do you know where this is? Does anyone know where this is? Yeah. So this is the computer science building at MIT in Cambridge, Massachusetts. A few years ago, because at MIT there was always a difficulty between computer science people and artificial intelligence people. And at some point they decided that this is not a very good thing. They should work together, have social interactions, create an environment where there will be social interactions. So they spent several million, maybe a couple $100 million to build this building to house both computer science people and artificial intelligence people, and create areas where people can randomly run into each other and interact, so that good ideas will come about. And MIT, you've heard of it, so it's a very prestigious place. They know what they do, and they hired Frank Gehry, one of the most famous architects of this century, last century, this century, and to do this building. And unfortunately, after all this money and all this work, first of all, it was late. Okay, I went there for the opening, and it was a construction site, and you couldn't actually go there. So it was late. So and then they have these problems. So MIT is suing Frank Gehry, claiming that design and construction failures, in pervasive leaks, cracks, and drainage problems that have required costly repairs. So this is, I think, pretty bad for a world-famous architect to build a building for a world-famous institution and to have problems of leaks. I mean, you would think that it's a new phenomenon. I mean, when we deal with software and we build something for spacecraft or something, it's a completely new thing. We don't know what we're doing. But leaks in Boston, in Cambridge, you know, this guy, even in this picture, this guy has an umbrella. So it does rain there. And the architects must have known that. I can't imagine how nowadays people can build buildings that will have leakage problems. So I think that's not good. And they're dealing with some physical object, not even an abstract object. Here's a less famous building. This is actually the Congress Hall in Lugano. Lugano is a small city. You know, we didn't have Frank Gehry. Somebody, I don't know who designed this thing. So it's a Congress center where you can have meetings, but it's also a musical hall. So you can have opera and symphony and such music. And it meets the minimum requirements. That is, it has seats, so audience can sit in the seats. And it has a stage where the speakers or the singers, the musicians can be there. Unfortunately, it has some problems with poor acoustics. So, and that seems to be actually a common problem in music centers that they build these days. Well, you say, okay, they must have known that the purpose of this building was for symphonies, for example. How can they create the problem with acoustics? A more serious, for me, problem is this is my building, computer science building in Lugano. The faculty is new, and at the very beginning, you know, they promised to build us a new building, and one of the things I wanted, actually, was a building that would encourage collaboration among people. If you're familiar with the European model of universities, at least the German model, you know, each professor has his own center, and they work by themselves. There's not much collaboration among professors. So what I really wanted here was a building where there would be areas where people could collaborate, similar to the MIT idea. And this was told to the architects, to the builders, and they came up with some ideas. And it was built almost on time. Unfortunately, this building has, again, I mean, it's a building, so it has offices in it, has room for students and professors, but the air quality is very bad. And that's okay. The lighting is very bad inside, and acoustics are very bad. So there are these three major points that don't really help in collaboration and getting people to work together. And these are especially bad. Again, you know, I showed you in Boston, they know it rains. They have leakage problems. Here in Lugano, we have sun all the time. We have very good air quality. But inside this building, we lack both of those. So, like I said, these things. So, you know, this is what actually motivated me to develop this talk. because I said, how can these people make these mistakes? We, in software engineering, for the last 40 years, we always say, oh, we are so bad, we make all these mistakes. Let's look at engineers and see how they do things right so we can copy them. And here I was seeing example after example of so-called established disciplines making bad mistakes, huge mistakes. So how would a software engineer approach this problem? We want a problem? Encourage collaboration. Now, I must say, it's not a simple thing. It's not like, we expect miracles from them. Even the idea of collaboration, what does that mean? In computer science, in computing, we have had people whose research work is collaboration. So trying to define what it is and develop support systems for collaboration. So how would we approach this problem? First thing a software engineer would do is would try to define the term. We can't just say, oh, collaboration, let's build it like this. We have to see what it means. So maybe very simple thing. For any two people, PI and PJ, they should be able to communicate. I mean, fine, this is very simple. But at least it's a step towards trying to define what collaboration means. Of course, in software engineering, we have people who go off and talk about theory much more than what practice. But, someone might say, oh, but people are mobile and they move around, so we can model them with mobile processes. So let's use pi calculus, because that's the best theory for dealing with mobility. Or use temporal logic, because collaboration takes a certain amount of time, and we want to say eventually the collaboration will take place. Okay. But we have developed techniques to specify clearly what problems are, what is the problem, and then find solutions to those problems. Unless you define what the problem is, you cannot solve it, because what are you solving? Maybe in trying to define this thing, collaboration, you will discover that, oh, but for PI and PJ to communicate, they should also not disturb PK. So two people may be able to communicate, but this should be not across the room yelling at each other, because that disturbs other people. And in fact, that is exactly what the architects have developed. There are these huge tables with many chairs around them. They think, okay, they will sit there and talk to each other. But two people can talk to each other and disturb the other ones. My point is that by defining what the problem is, we can try to uncover hidden problems. And in software engineering, there's this effort on requirements, elicitation, and engineering that has been very important for developing reliable software. So in the software engineering solution, in general, we have functional requirements. We say, for example, the building must have rooms, must have a place to work, must have places to meet, must have bathrooms. I mean, this is an example, a very extreme example of this is when they built these soldiers' barracks outside of Vienna, like 100 years ago. They forgot to put bathrooms in there for soldiers. So it's important to list all of the requirements, but these are only functional requirements. And we know in software that we also have quality requirements. So some things we can say exactly, and some things they have levels and degrees. That over time we have found out that these things cannot be very objectively specified. So we have metrics. We have tried to develop standard quality attributes and metrics for those attributes and how to measure them. And these are very important for buildings, any kind of product that has a social component. And buildings are exactly that. Buildings bring people together. And so we have to be able to to satisfy, keep the people happy in these environments. Not only useful, but also user-friendly. So this idea of function and quality, functional attributes, or some people call them non-functional requirements. I prefer the quality requirements because they always actually deal with quality attributes. So this is a fundamental discovery in software that we rely on to develop software that not only works, but it is, it's not a joy to use, but stays out of the way and makes its functionality available without hampering the user. Well,
do you mind comments on the way, or you want to?
How much time do I have? Depends on that. 1.5 hours. Okay. No, I think because it's actually there's a sequence of ideas that I'd like to get across here. So in the architect world, they actually have also kind of faced this issue of function and quality, but they call it function and form. So there's been this discussion in the architects world about function versus form. Which one is more important? And this Louis Sullivan, an American architect, he was very adamant that actually form should follow function. So first you decide what the functionality is, what is it that you want the building for, and then you build around that. So this is one building that is an example of this idea. It's not very beautiful, but it satisfies its functionality. There are these three guys, Mies and Gropius and Corbusier, who is both French and Swiss. I was corrected once when I was talking in Switzerland, and I told them it's a French architect, but they said he's Swiss. So these guys are known as the masters of modern architecture. So modern architecture, you can classify it as like skin and bones. Don't put too much frills around the building. Not too much. Don't worry about form so much. Less is more. God is in the details. You have to build it, but the details matter. So in the Frank Gehry building for MIT, it matters that even the walls are such that they leak. I mean, it's maybe a little thing as far as Frank Gehry is concerned, but for the people who actually work and live in that building, it's a big issue. Maybe Stan recognizes this. So one of the guys who was very central to the idea of not worrying about form, what matters is function, was Adolf Loos. He was Viennese, and he in fact built this building, which is known as building without eyebrows, because in those times you always had called stuccos over the windows. There's always some decoration, something. And he said, why do we have that? That's really not a good thing. Is anything that is not necessary, let's not have it. So he built this building, and it was a scandal. In fact, the government office is like on this corner, and when this building went up, the emperor said he will never again come to this square because this building is so ugly. It doesn't have any kind of beauty, any kind of form. Well, Adolf Loos went very far in his idea. In fact, he has a very famous essay called Ornament and Crime. So he says making buildings ornamental, putting things around it, things that don't actually address the functionality is a crime. You might think it's silly, but his point was, if you have people's brains concentrate on frills, on decoration, things like that, they are not working on what are really substantial issues. So they just work on form instead of function. So there was a big, discussion among among architects about this thing since that time. This idea of crime, you might even, let me go a little bit further with that, because it's not so silly. When was this one? In 88. So in 1988, this civilian airliner over the Persian Gulf, Strait of Hormuz, was shot down by a Navy ship, a U.S. Navy ship. And all people on board died, of course. And when something like that happens, it's a serious issue, and it's very hard to find out what is the real cause of this. What was the reason for this happen? Especially when the two antagonists, the U.S. and Iran, the bad relations, so everybody blaming everybody else. So what is the reason that this happened? So, well, if you look underneath the Navy ship, inside the control room, this is the interface to the system. There's these young people sitting there in front of lots of monitors that tell them what is the situation outside. So there are airplanes coming. These airplanes are friendly. They're not friendly. And based on all this information that comes there, they have to make a decision and tell the captain or whatever it is what to do, or what is the situation. And there, as I said, who knows what the real reason was. But at least some people claim that the user interface, poor design of the user interface of this system contributed to this incident. That is, it was not easy to tell, actually, that this airplane was a civilian airliner. So form versus function, it satisfied its functionality, shot down an airplane, but maybe the form got in the way and shot down an airplane that should not have been shot down. So this idea of form versus function, whether spending time on functionality or form is crime or not, it's really something important to keep in mind. Only recently I saw this article in the New York Times about a new building that was going to go up in New York. And they have given it to Norman Foster, again, a very famous architect. He says he's going to do this and this and this. And the last quote in the article says, this Norman Foster says, to be an architect, you have to be an optimist. You have to be a realist, of course, but you have to be an optimist. Well, as software engineers, we can't be optimists. We can't be optimists. I would like to be an optimist. But if you're going to build a building that people are going to go into and use, you can't just hope that it will satisfy their needs and their quality requirements. You have to really think about how to satisfy those even quality requirements, not just functionality requirements. When we build software that's supposed to work all the time, we can't be optimistic and say, oh, the user will kind of understand what this is, we hope. Okay? So if you send an SMS, you want it to arrive. You want to just say, okay, probably it will arrive. So we can't be optimistic. And neither should architects be. So in software, we don't do this thing. We don't say form versus function. We require form and function. In fact, and there's some really nice examples. Here's form and function. Google, very simple form, okay? Just a little box. The functionality behind it is huge. It meets a lot of requirements. they didn't go around, all kinds of bells and whistles, buttons to press in order to choose the functionality you want. Just form, very simple form. Simple form is much better than ornamental form. And of course, I always like to show the iPod because that's a beautiful example of function and form. Okay, it's very simple. No buttons. It's very, very simple function, simple form. There are many other devices that do exactly the same thing, but their form is what I think defeats them in meeting the requirements of what people want from such devices. So back to software. Stan mentioned this book that Carlo and Dino and I have written. And actually what we did is we tried to say these are the software principles. These are the principles, 7 principles that we use in software development, software engineering. That's what everyone in software should know about. Now it's not, there's many things you have to learn if you are doing software. Languages, specification languages, logic, whatever. But behind everything else, there are these 7 principles. And we summarized what people knew already. It's not, we didn't invent these. These are actually known, in all science. Well, not all of them, but certainly being formal and rigorous, that's the first thing. So you can't just optimistically say, oh, I will make it beautiful like this, and it will probably meet its requirement. We have to be rigorous and formal. Abstraction is the basis of all science, so that's nothing new for software engineering. Separation of concerns. We have to deal with different issues because we have many issues to deal with in building any kind of complex product, software or not. We need to concentrate on each concern as much as possible separately, but of course the concerns are related. So we have techniques for minimizing the interactions of these concerns. Modularity, but so incrementality. Maybe I'd like to spend a little time on that one, because this idea of incrementality is what we discovered back in the 60s. That is, when people started to build these large projects, they did one little program and they say, oh, now we can do airline reservation system for American Airlines. And we have discovered from then that you can't just do this big bang approach. You can't build a whole thing, the whole system all at once. And the best way to approach this, the building of a large system, is to go incrementally. Incrementally at building its requirements, but also the system. So slowly build the system. This agile programming does the same thing. Extreme programming is the same, some ideas in that regard. So we incremental approach to building complex products. This is a very important thing in software development. And I think others, even building architects, could benefit from that. I know there are some projects that people are figuring out how they can build buildings incrementally and try them out before taking the next step. And I think some of the ideas of those modern architects, modern 100 years ago, about the skin and bones, that is, first build the outside and then slowly build the internal structure, the details, put the details inside. That has something to do with this incrementality idea. So generality says that sometimes building a more general software is more useful and easier than customized software. But of course, this is not it's not always the case. And it's a very difficult choice to make. Should I make a custom-made solution or a general solution? And anticipation of change. We know with software we have to build it, that it will grow with the user, with the requirements, with the environment. And so, and I think this is true about buildings as well, about other products as well. In Europe now, actually, many buildings that were built after the war, they have to be reused, either torn down or reused for new purposes. And they're facing exactly these issues that they never thought about before. It's just, I think it's the same thing we faced earlier. That is, we would build a software and say, okay, this is it, go use it. And then we discovered, well, things change. We have to evolve the software evolution. And it seems like buildings in cities definitely face the same issue. So I think I can stop here if you want to ask questions. But I have more to say. But this is a good, because I think my first part of my story is finished here about form and function. And I have more to say. But I don't know. Should I go on?
Any questions?
Or comments or something? Okay. So another important thing, I think, in software engineering, that in software development, that we have found is about process. So early on, there was kind of a chaotic process of software development. You know, managers would say, let's build this system, tell the engineers, and the engineers would go around and say, okay, let's build things. And over time, we realized that, well, that's not going to work. We need some kind of a more disciplined approach to developing software. We need a process. We need to go through some organized steps, not just let anyone do whatever they want. On the other hand, the problem is people are not interchangeable. So you can't just build a process and say, okay, I put 5 people here, 4 people here, and things will work. Because people really are not interchangeable. Some people are 100 times better at other people than other people in some things. So maybe somebody is a much better coder, somebody is much better analyst, somebody is a better tester. Well, you know, some people are not good at anything, so they shouldn't be doing software. But for sure, people are not interchangeable. So that's a big deal. On the other hand, we have organizations that need to develop software that is reliable and correct and inexpensive. So somehow we have to organize these people together. So what is the role of process in this in developing software? Process and organization. The good news is that organizations, in fact, can improve, even though they hire people who are not interchangeable with each other. So if somebody leaves, you have to get someone else, and you know that you're not going to really replace that other person. Still, as an organization, they can improve. And this is, I think, initially when this idea of capability maturity model was introduced, I was very skeptical. I said, oh, come on. You know, I guess maybe I was young at that time, and I thought, oh, people are the most important thing. And of course, people are the most important factor in software development. But organizations are also important, and they need to be able to put the efforts, the contributions of different people together. So this idea of capability maturity model says that, you know, there are different levels of maturity. Are all of you familiar with this? Okay. Okay. The idea is that there are different organizations, and each, just like kids or people, you know, we start to crawl and then run and then, no, crawl and walk and then run. Organizations are also the same. At the beginning, when they start up, they are at a certain level of maturity. They can, you know, they have some, they can develop software, but maybe not as reliably as other ones. Some other organizations are much better, are predictably. They always develop their software in a predictable schedule, and they meet their requirements. They deliver on time. Other ones are even more mature. They improve all the time. So this model developed at Carnegie Mellon University says that there are actually 5 levels of maturity. At the very bottom, there's actually nothing. It's just a bunch of people. Each time you give them a project, they go about, and maybe they develop the project or not, but there is no predictability. You don't know. Okay. Then the next level is a managed one. So each project starts with a process. They develop a process, and according to the task they've been given, they develop it, and then they deliver it. So again, you can't really predict because it depends on the particular project. And level 3, which is the most common maturity at organizations now, is that the whole organization, there is a process that says the organization will follow this process. And then each time there's a new project, they customize that process to that particular project. And the other ones, the level 5 is they measure their progress for each project and they reflect this back into future projects. But this is great news for organizations because it means that they can measure how good they are, and if they want to improve, apply measures in order to improve. Even though the product they're developing is abstract, it's developed by people who we don't know really who is good at doing it, who is not good at doing it. But still, as an organization, we can bring a team together to develop software better. So, I don't know. I saw this in France a few months ago. I was in France, and I saw this. It's a parking meter. So it's a parking meter, and it's great because I used it as an example. I wanted to use it as an example of poor design, maybe, because these things are written by hand there. Okay? So, in fact, the engineer who developed this thing, the user interface, he thought was very intuitive. He or she thought it was very intuitive, I guess. There's a hole where you put coins in it, and there's a red button for pressing and a green button for pressing. But apparently it was very easy to customize because in this particular town, somebody wrote, if you're a bus, you follow steps 1, 2, and 3. If you are a normal car, you follow steps 2 and 3. And then they labeled 1 is over there, so that's for buses. 2 is over there for coins. And 3 to say confirm, and red for cancel. So, the design was there, and it was just customized for this particular implementation. Happens to be in French, so if it was here, I don't know, it would be in English or whatever. In fact, the details do matter. So if you build a general product, then you can it can be useful to people. So I've been watching development of software engineering last few years, few decades. So I think it's interesting to look back and see how we got to here. Again, my message is software engineering is hugely successful. It's maybe not recently, but it was very common until a few years ago. You go in software engineering conferences and people are always lamenting, oh, our software is so bad, we make so many mistakes. But as I told you, it's because we look for mistakes, and we actually, that's part of our job. Instead, I think software has been hugely successful. And if we look back at the history, a very, very brief history of software. So in the 60s, there was the idea of a software crisis. All projects were unsuccessful. Many projects were canceled. Most projects would be canceled. So the term software crisis was coined. And in the 70s, in answer to this problem of the software crisis, a lot of effort was spent on software process. And I think the reason for that was that it was the managers who were unhappy with the situation, with the software crisis. The engineers were great. I mean, they said, oh, there's all these projects we were working on. It's fun. And, software was new. People were enjoying working on them. The managers who had to deliver the products were in trouble. And they said, no, we need processes in order to make these engineers work and deliver software as opposed to just have fun. So in the 70s, there was emphasis on software process, and many models for software process were developed. And that, of course, did not solve the problem, because we thought they thought that would solve all the problems. So in the 80s, the university people mostly, they said, well, we need some theories. It's not just put a bunch of people there and give them some processes and say, follow these rules and they will develop software. We need some theories. So in the 80s, there was a lot of theories on methodologies, on formal methods, even efforts to prove correctness of software, because we wanted to have correct software, and verification of software. So the emphasis was on that. That also did not completely solve the problem. So in the 90s, people said, well, theories are great, processes are great. Actually, people didn't say it like that. People would say, oh, processes are not solving our problems. Theories are not solving our problems. What we need are tools. So there was a lot of effort on tools, developing computer-aided software engineering tools, in order to at least make some of those theories that were developed, and also some of the processes that were developed, usable by people and organizations. And I think that putting those three things together, that is processes, theory, and technologies, is what this combination has enabled software engineering to evolve over time to be a very successful discipline. In the noughts, in this decade of after the 90s, I think the emphasis has been, at least for me, has been on how to interface the software to the world. Okay? There have been two areas actually where people have worked on. One is sensors. That is, now we have all these devices that are embedded in the real world, and we need to monitor them. We need to invoke them in order to react to what they see. And so there's been this has introduced issues of scale and interaction actually with software. So a lot of effort is going on in this area. Another is that more and more people are actually interacting with devices, and not necessarily computers, but devices. And so how to include people in the ecosystem that consists of the software and people. So social networking sites, for example, are addressing these issues. And now we are in 2010. I don't know what I mean, I have projects in these two areas, so I don't know what the next 10 years will bring. So if I were to conclude with just a few lessons from software engineering that, actually in normal everyday life we can use, but certainly in other disciplines they can use, is you have to define and prioritize your goals. So it's important to know what the goal is, define it precisely, and prioritize it, because usually you have more than one goal, and you have to see which one is more important. You have to pin the requirements precisely. Know exactly what it is that you're trying to do. Not just, oh, we do this and a little bit of that. You have to know exactly what you're going to do. Separate functional from quality requirements. I've talked about this a lot. Since typically it's not one person doing this thing, there's a group, a team, we need to improve the organizational process and capability. And there's a lot of efforts in this agile work and open source. All of these address this kind of issue. The next thing is look for bugs. We have to look for bugs. And if somebody finds a bug in what you've done, you should appreciate it. You should say, oh, thanks, as opposed to say, oh, say something else. Okay? So look for bugs and remove their causes. Okay? It's not enough to just remove the bug. And know that bugs may be caused by process, method, or human error. So it's not a simple thing. Now, since I have a little bit of time, this issue of we've done great in software, so it's very easy to stand and say, oh, we've done great, but always in software engineering conferences, as I said, there's discussion of, but we still don't have perfect software. And so what is the problem? I mean, we keep progressing in software engineering, but software still crashes and fails, and we have a lot of software problems. People go around in this discussion. This is my answer to this dilemma. Even though we've made a lot of progress, we still face problems. So what should we do? And I think that engineering is about compromise. When you build something, just like those architects, when you build something, you have to make compromises. You can't do a perfect thing. But in research, we look for perfection. So our theory is about perfection. So as engineers, we don't really produce perfect software. We try our best, but we have to make compromises. But in research, we must look for perfect software. So in research, we have to look for how to develop perfect software, whereas in engineering, we can't. We know that we can't do that. So related to what I've talked about here today, there are actually there's some other discussions. So Jeanette Wing has been pushing this idea of computational thinking. Her point is also that what computer scientists, so her emphasis is with computer science, that we have developed a lot of theories in computer science that is actually useful for everyday life, and so this should be taught at the first year of university and maybe even in high schools, this idea of computational thinking. I think it's a little bit too far-fetched what she's proposing, but anyway, that's another opinion. And Peter Denning disagrees with her about, we need to go beyond computational thinking, because computational thinking is only about, maybe simplistically, emphasizes algorithms, and Peter Denning says that actually problems are much bigger than just algorithms. We have to deal with the whole ecosystem that includes people, and so we can't only think computationally, think about algorithms, but how they affect their environment and people. So I think this, I think maybe our field is mature enough now that we are trying to figure out how we can benefit other disciplines as opposed to just copying from other disciplines to improve our race. So that's what I have to say. Thank you very much. And yes, please.
Yes, I have one question.
Yes.
Let's say we have built a system for a long time. This is a big system. Then we find out there's a bug. That's good. And we know how to solve it. But the point is, the solution could introduce a new bug. This is bigger bug. What do we do in this case? Do we leave the old bug or we solve it?
We live with the bug, or we? Well, often this comes out to be a business decision, because, anytime you introduce new software in order to fix a previous bug, we know there is a risk of introducing new bugs. And, there are methods. We can do testing, we can do analysis to make sure that we don't introduce any other ones. But if the system is big, the interactions with the other components is complicated. So it's risk management. I guess that some business people have to decide what is, or engineers as well. It's a matter of what is the risk of not fixing the bug versus fixing it. I don't have any magic answer to that, of course. It's a serious issue. Actually, when I was working at companies in software development, we had weekly meetings of managers, and we would go over the bug list that had been reported in the previous period, and we would rank them. We would say, you know, this one is important, and you know the reasons could be different. Could be important because it's an important bug, or because it was reported by an important customer. But we had to rank, you know, which ones to work on. There is no. In those processes, there were no systematic ways of doing it, but but there are systematic ways of doing risk analysis and risk management. Us meaning who? Yeah, system builders and their managers. Yeah, because the managers are also involved. Yes?
Do you think it will be perfect one day to reach a perfect software? Do you think it will be possible to reach a perfect software one day if, I mean, after 2,000 years or 10,000 years, the architect didn't even manage to make something with a click?
Well, if it's 2,000 years, I don't know. But probably not. You know what? Because the requirements keep changing. You know, now we can make perfect software for software that was built in the 60s or 70s or 80s, maybe even 90s. But requirements keep changing, and environments change, so we have new devices. We have, yeah, so... Yeah, it's not that the software is buggy. It's that we don't know how to deal with the requirements.
One of the fundamental differences also is that it's quite easy to make the software evolve and change. I mean, if
Right.
you can correct it. If the building is structurally flawed, you have
Right.
to break on.
Exactly, yeah.
Is it worth it to try to do a perfect software?
Well, it's a engineer. It's a compromise. You have to decide. You know, how much will a failure cost you? So if you know, if you're sending the space shuttle into space and it explodes because, or the Ariane 5 that you know, instead of using 16 bits, they used 8 bits, or the other way. Instead of using 32 bits, they used 16 bits, and the thing exploded after 30 seconds. So it was a big. Bad decision on the part of the, yeah. I mean, it's the same thing that he said. If the system is complex, it's very hard to know what the impact will be of the. But in the sense, in the thing that you said about buildings, if they are fundamentally flawed, then you know, if the foundation is wrong, then there's nothing much you can do. That's the same. We have faced the same thing in software engineering and the work of Dave Parnas, which I hope you all know. One of the things he says is, you know, program families, that the most important design decisions should be made first, and those are the hardest to change. So if software also has foundations, and if you want to make a change in that foundation of it, you have to change the whole software. Yes?
Relationship between software and hardware, because these two things are developing parallel.
Yeah.
It looks to me that this hardware is developing very fast, and also changed, for example, from this mainframe desktop and to these embedded mobile devices. So
right.
How much actually our students should know about the hardware in order to be a good software engineer?
So the relationship between software and hardware, and yeah, it's true. Hardware is moving fast, advancing fast. Although I think it's easier to measure the advance of hardware than software, and software by nature has to follow. When there's new hardware, software has to follow that. So now with this multi-core developments, again, there's a revival of traditional fields in computing, you know, like compilers and operating systems and databases, trying to take advantage of this multi-core systems. You know, if you look at the pyramid, I mean, the hardware is the reason that software advances maybe are not as obvious is that we have developed these layers of abstraction. So we try to hide as much of this hardware as possible. So new hardware comes, we just plug it in at the bottom, and our old software still works. Now, of course, there's generational changes. So when the software really changes, when the hardware really changes, then we have to rethink the software. On the other hand, we have all this investment in current software that we cannot really change it. So this is really faced by in scientific computing, where every 10 years or so, there's a new architecture which completely is so much faster than the older ones that people want to switch their software to use this new hardware. But it takes years to develop the new software for the new architecture. So I think to get back to the real question of how much should we teach the students, the point is that majority of the students will probably work at the higher levels of software engineering, so that they don't really see the lower level hardware issues. But of course, if they are at this layer of hardware-software interface, then they need to be expert at the hardware issues. That's a very interesting point. Right now, one project I have is we are dealing with devices. So we're using the web to control devices like robots. And we had, in fact, to get master's students from the electrical engineering department to do the low-level programming of the device, to build an API for accessing the robot, because our normal computer science students were not really capable of addressing that issue. So maybe it'll be good. We'll get closer to electrical engineering again. Maybe it's my age, but, well, it is definitely my age. But in the old days, everyone had to learn, everything. Computer architecture, operating system, databases, compilers, languages, But now we deal a lot with applications as opposed to...
Yeah. In other words, for the majority of the software engineer, we just treat the hardware as a black box.
Yes. Yeah, with an interface. Yeah, I think maybe that's the field. The embedded systems, people who work in embedded systems need to definitely deal with hardware and software. But other people in other domains, they don't need to as much. But you should know that maybe in 10 years, the architectures will change and all that we know will become obsolete. So it's unlikely that it will happen because of all the investment in software. Companies, organizations, we don't really want that to happen. So we always find some way of introducing the hardware underneath without impacting the higher level issues. So yes, I think the majority of the students don't need detailed knowledge of the... I'm very uncomfortable saying that because nowadays, even if you write an application in Java, there's so many, and let's say you have poor performance, there's so many layers of the virtual machine, the paging, all these things interact with each other, and unless you know what is underneath, you can't really do the performance debugging that you need to do. I don't know, some other rambling response to this question. Yes. Yes?
So what do you consider to be good software benches that can be used by programmers?
Software what?
Like IDE and so on.
Oh, there.
In your opinion, over the years?
No, you know, that stuff keeps changing. So Eclipse, for example, used to be great a few years ago, but now it gets complex, more complex. I don't know, it depends on the project. Did you mean students? Did you say students or? In general. Well, those are so much application dependent. So much application dependent because, you know, if you're doing enterprise applications, you know, there are, you know, different frameworks. Yeah, I don't have any product endorsement, but they really are application dependent, and it depends on the knowledge that you can find from you know, in the market when you're hiring people. I was, yeah. I was actually, I talked to a company in Australia a few weeks ago, and they said that they had to do their work in Java because they could only hire students who were trained in Java. They couldn't find students in, you know, in C or C++, for example. I mean, it's crazy, but.
And those students couldn't learn C, so this would be really.
Oh, it's real.
Java, and they wouldn't be able to learn another thing.
It's a real, yeah, I think it's a real problem. I mean, we do have this problem actually in education because some universities I've seen, I mean, they've become so Java oriented that students cannot handle the lower level C, and I mean C. To me, that's really important. So, yeah, I don't know. How about you guys?
Following up on Wayne Gunn question, like if you take a paradigm, you can do command line. I'm trivializing. Command line or ID visual way.
Yes.
There are still quite a lot of people who prefer to the command line.
Yes.
For example, with Microsoft. They don't use any IDs, they don't see any value. So it is not such a, shouldn't be taken totally for granted that all those visual things necessarily, you know, are commonly accepted and are necessarily very valuable. Do you have opinion on that?
Yes, I do have an opinion, but not very successfully validated. Because when we started the faculty in 2004, so we did, basically I developed the curriculum. And one of the things we had was like part of the curriculum, which is very interesting, is half of the time the students work in practice-oriented work and half in theory. So the idea is they have courses, and then in the afternoon they apply the theory in practical projects. And from the very beginning, we wanted them to use command lines. So we actually wanted them to learn about the shell, Emacs editor, and of course at the beginning when all these people came from high school, they said, "Oh, yeah, I know how to use Word," and that's it. And you know, you ask them to type a program, and they would use Word. So I don't know, you're laughing because you've seen this yourself, or you think it's funny, because it was very sad actually. So for a few years, we really emphasized teaching these lower level paradigms because, because you know you can start with IDEs and you don't really understand. And we use Macintoshes, and so people hardly ever need to use a command line. You know, everything is visual. But now we have the problem that our new professors are the same. That is, they say Emacs, what's that? So so it's. I think it's a problem, but I don't know. Maybe you know, maybe it's just it's some kind of progress, and I believe that people do need to know command lines. They need C. And they need even Emacs, because it's even underlying many of the tools that you see in the Mac, which is very visual, are Emacs commands. So that's my opinion. My opinion is those are important.
I think there is a point in this bill. If you know only IDE, and then there is plenty of stuff generated from you, you have no idea what's in between.
Right.
eventually at some deep stage of software development you can come to a big problem. If nobody in the team knows what's
Yeah. No, in particular, yeah. In particular, in performance debugging, students are completely lost in why is this software not performing well. So we have a course actually on software performance at the master's level. And we give the students like 2 programs and say, why is this one better than this one? And it's very challenging for them to find out what goes on. Yeah, the more you hide, the less people see, of course.
Any other comments, questions? Maybe I have one.
Yes?
There was this slide you were talking about the importance to define terms, things, because otherwise we don't know what we are talking about.
Mm-hmm.
Right? So it boils down also to maybe some of the successes and failures, both in engineering and in software engineering,
Mm-hmm.
because you don't define precisely. But there is a danger in this,
Mm-hmm.
because if you define too early, if your definition is
Yeah.
incomplete wrong,
Mm-hmm.
then implications may be terrible.
Mm-hmm.
In your slide there was, I know that's an ad hoc example,
Mhm.
but you were defining collaboration.
Yeah.
And the definition was any 2 people should collaborate.
Mm-hmm.
So now I might build discussion rooms for 2
Right.
people only. But in fact, the intention is that 5-10 people should
Right.
collaborate.
Yes.
I should have discussion rooms for 10 people too, right?
Right.
So let's say that you stop at some
2. Yeah.
intuitive understanding, but you don't go deep enough.
Mm-hmm.
And then after 2 or 3 weeks, 2 months, you take this definition
For yeah, this is a danger.
It's the source of many, many problems in software.
Yeah, yeah, yeah.
Forget about engineering, but in software development.
Yes.
What is your...
There is definitely the danger of that you take the thing that's written down. But I think that's the best we can do. I mean, you have to, when you're working, you have to be working according to a specification. And the specification has to be written down. Because if you don't write it down precisely, then I don't know what you're doing.
Yeah.
So maybe we need some kind of mechanism to go back and review these specifications. Yeah.
Like this incremental development.
Right. Oh yeah, the incremental development also applies to requirements and specifications and all that. And of course we know that we have to go iteratively over these increments. Yeah. Right. I have one more slide to show you about prioritizing goals. So I saw this clock in a bar. So when you're in a bar, having a clock in a bar is kind of a dichotomy, because why would you have that? So this was all the numbers were at the bottom, because actually who cares what numbers show? Yeah. So thank you very much.